Hello everyone, thanks for joining me here. Now I will talk about our recent work on active prediction for discrete event patterns. This is joint work with Stefan R., Seja Dat, Stefan Shaw, and me as well. So I will very briefly talk about the motivation as well as contribution of this work. The system that we study is a partially observed and controllable system. For such systems, it's very important to construct the mapping from observations that a controller can obtain to control actions that controller can decide to guarantee the considered properties, such that system can always stay in the desired states. And we can see everywhere in today's life for such systems, such as automobile, plane, trains, as well as modern industry systems. For example, for Industry 4.0 systems, new controllers are required. Well, it is proposed that the hardware of a controller should contain sensors and actuators with a control program distributed as a smart service on the network. I'd like also to talk about diagnosis prediction. In medical terms, actually diagnosis is to identify disease based on symptoms, and prediction is to predict future possible diseases as well as outcome of treatment. Clinical prediction rules are widely accepted, which is mathematical tools that identify and quantify the contribution of important information such as symptoms to a specific clinical scenario, which can help making some prediction. So this is very similar for system diagnosis prediction. For a partially observed system, diagnosis is a task to detect fault that did occur in the past based on observations. Prediction is to predict future fault that will occur also based on observations. So two corresponding properties. Diagnosability is a property to diagnosis without any ambiguity for every occurred fault based on observations. Both passive and active versions started. Active diagnosis is to synthesize a controller based on observations to keep the system stay within a subset of diagnosable behavior, and predictability is a property to predict with certainty all future fault occurrences when systems still in normal states. For this property, only passive predictability has been studied. In this context, we active predictability with several contributions. So first, we refine predictability by formalizing the lower and upper bounds for prediction, and we introduce active predictability by characterizing the requirements for controller to guarantee this property, and we prove the equivalence between active predictability and the existence of active predictor, and then we focus on decision synthesis problem, for which we prove that active predictability is exponential time complete. We show how to construct active predictor through a winning strategy of turn-based games. Finally, we established a relationship between the prediction bound and the number of system states. Next, I will turn to active prediction. So the model that we use as label transition system, which is classical one, except that we divide the set of events into two distinct subsets, observable and unobservable, and the faulty event is unobservable. Then we adopt the two conventional assumption leftness convergence. Systems life if from each state of the systems have at least one outgoing transition, and convergence guarantees the non-existence of an infinite sequence of unobserved events. Now let's look at this example, which is a LTS model, which is live and convergent. So we use the dashed flash to represent unobservable transition, and depends on what events in the sigma 1, sigma 2, this system can show different level of predictability. I will return to it later. And so what is predictability? Now let's look at this set of behaviors of a given system. We use blue to represent observed events, and orange to represent the fact that both are the same observed events, and red to represent the faulty event, and purple color to means that this corresponding behavior is normal. So a system is predictable if faulty behavior can be predicted before their occurrence. So, in other words, observed sequence can forbid fault prediction if we still have possibility to have infinite normal future behavior. So, if we observe this part of events, this one is the observer events, and just before the occurrence of this fault, and from here we still it is possible have the infinite normal behavior. So this the current this fault is not predictable, and the system not predictable. And next, when we look at this system, this is also represent the normal behavior. When we observe this three observed events which exclude the normal behavior, so we know that fault will necessarily occur, and so it is predictable. But for predictable system, we can do better. If we observe the three observed events, and if we further know that the fault will occur but within k and k plus l further observations, and if every fault can be predicted in this way, the system is KL predictable. If these three observed events are ABC, so the observed sequence ABC, we say it is K correct K plus L40, which means that when we observe ABC, we know that system will keep in correct state within K observations, but will necessarily become 40 within K plus L further observations. So if a sequence is K correct and K plus L40, such as ABC that we did see before, and such observed sequence we say that it is KL40, and given LTS is actually KL predictable if for every faulty behavior it has a observable prefix that is KL40. In this way, we can guarantee that every occurrence of fault can be predicted in advance within K and K plus L observations. Now let's look at this example. For the first case, we have at least one common event between sigma 1 and sigma 2. Suppose it is A. So when we observe ADF is a faulty behavior. So this faulty behavior has no observable prefix that is KL predictable, because whatever we observe, such as empty A or AD, it is always possible to have an infinite normal behavior. So it is not predictable. But when there is no common event between sigma 1 and sigma 2, such as here is A, here is B, and when we observe B, we can be sure about entry into Q1, where we also be sure about a future occurrence of the fault. The fault will occur necessary between 1 and 2 further observations, so it is 1 predictable. And when we consider controlled LTS, so the set of observed events is divided into two subsets, controllable and not controllable. So a controller is actually a mapping from observable sequence to a subset of events that are allowed for next step by forbidding a subset of controllable events. So in this way, controller can restrict the behavior of the system. Consider this example now. If the controller decides to forbid the occurrence of A when he observes nothing, which means that we stay in the state Q0, and in this way, the two first transitions are valid in the controlled LTS. In the controlled LTS, actually each state is composed of observable sequence and a system state. So when we in this state, B is possible, and after B, the observable sequence becomes B, and we enter Q1, and similar for C. But these two transitions are not possible because A is forbidden when the system in Q0. Now I will talk about semantics legal predictions that we define. So therefore, we use top to represent fact the controller cannot predict a fault. And KR means that the system currently correct, but fault will necessarily happen between K and K plus A for the observations, and question mark with M signify the fact that fault either fault has ought will surely occur within M further observations. If a fault has already definitely already occurred, then we use the button for the prediction. Now let's look at this example. And when we observe whatever number B, we know that we stay in this Q0, and we cannot predict fault because we can infinitely execute B. And when we observe A, then we know that we enter these two states, and fault will necessarily occur between 0 and 2 further observations. And when we observe furthermore D, and we know that we are in these two states, and for the fault, either fault has occurred or it will occur within one observable event observations. So it's question mark 1. Finally, when we observe A again, we know that these two states both are faulty, which means that fault has definitely occurred. So it's about button. We also formalize some relations that should be respected between two successive predictions with one additional observable event. For example, here, when we observe AB and the prediction given is the question mark and 3, which means that either fault has occurred or it will necessarily occur in further 3 observations. And when we further observe C, suppose both are C, then the next prediction is the question mark and 2. So either it has happened or fault will necessarily happen within 2 further observations. If only this one is C, so prediction becomes more precise because we know that only this behavior is possible. So the fault will necessarily occur between 1 and 2 further observations. If only this one is C, then we know that only this behavior is possible. So the fault has necessarily happened to such pattern. Let's look at this example. So when with the observation AB, prediction given is 2 and 2, which means that fault will necessarily happen between 2 and 4 further observations. When we observe furthermore C, both are C, then the prediction becomes 1, and lower bound is 1, the upper bound is 3, but if only this one is C, the prediction becomes more precise because only this behavior is possible. So fault will necessarily occur between 2 and 3 further observations. So we from all these examples, we know that once given a certain predicted window, such window will only become more precise with further observations, either maintained or shrinked. So this property can be guaranteed by the 2 rules. Lower bound prediction can be decreased by 1 at maximum, which means that it can be decreased by 1 or maintained or even increased, but the upper bound prediction can only be decreased. This is formal definition of active predictor, which is a pair of controller and a predictor. So the controller cannot introduce deadlock. Predictor should have the intended semantics that I described before, and we need to guarantee compatibility between 2 successive predictions. So we prove this proposition, the equivalence between the existence of KR active predictor and the KL predictability of the corresponding controlled LTS with leftness. Okay, next I will show how we handle decision and synthesis problem at the same time. So first, I will talk about controller knowledge update. To be able to verify active predictability, controller needs to memorize 3 elements: QC, QF, array states with or normal or faulty behaviors or consistent with observations, so they are deterministic, while P is actually non-deterministically decided by respecting compatibility between successive predictions. So now let's look at this system. When we stay in the initial state, so actually QC is always initialized with the initial state. So here's Q0, and QF is always initialized with empty, and controller choose the top as the initial prediction. And then when we observe A, we know that we will enter either Q1, Q4, both are normal states. So knowledge is updated as the QC becomes Q1, Q4, and QF is still empty, and then prediction becomes 0, 2, since fault will necessarily happen between 0 and 2 further observations, and these two predictions are compatible. And when current knowledge is here, and after observe D, and we know that we enter either Q2, which is normal, and Q5, which is faulty. So knowledge is updated consequently, and here prediction becomes question marked 1 because either fault has occurred or it will occur within one observed events. So these two predictions are also compatible. And when current knowledge is this one, and then after observing A, we know that we will either in Q3, Q5, both are faulty states. So knowledge is updated like this. QC is empty, and so consequently the prediction becomes bottom because a fault has definitely occurred. So these two predictions are actually compatible. Now I show you how to construct a Discrete game such that this game has a winning strategy if and only if an active predictor exists. A Discrete game has 2 players. One is control, another one is environment. Now let's look at this system. From the initial state of the game, first the player control chooses an initial prediction, which is here top. So this is considered as initial knowledge. And then game repeats the following steps. Control restricts the set of possible actions here. The set of controllable actions are A, B, C. So for this one, control forbids nothing. For this one, control forbids C. For this one, control forbids A, B. And the next environment needs to choose possible actions to continue. Possible actions are always constrained by the system. For example, if we stay in Q0, then A, B, C are possible. So here we see ABC, and the next control updates its knowledge in exactly the same way as I explained before. And this update also depends on which action is chosen by the environment. And next we repeat this cycle. Control again restrict the set of possible actions, and we continue in this way. In one future moment, we enter this state with knowledge as 4, which means that normal states Q2, Q5 with prediction and top. And suppose that now environment chooses action C, and prediction become now bottom because with C we know that only this faulty behavior is possible. However, top and bottom are not compatible. So in this situation, the game has to go into the last state, which means control is lost. And we need to find out other winning strategy. So in this way, we construct a Discrete game, and we prove also the equivalence between the existence of a winning strategy and existence of active predictor. So we prove that the active predictability problem for finite LTS belongs to expert time, and we also prove that this problem is expert time hard by a reduction from safety gain with imperfect information. So this problem is actually expert time complete. And finally, we also prove that for finite LTS, corresponding game can be solved in linear time with respect to the size of the game. Unlike in general case, the complexity is a polynomial. So this is done by reduction to reachability and safety gain. Actually, in this work, we also obtain some important boundary results. The first one is that given an LTS with exactly n states, then if it is 2 to the power of n active and predictable, then it is also actively safe, which means that if there exists a controller with which one can predict all faults 2 to the n steps before, then one can also avoid fault occurrence. This boundary is asymptotically precise because we prove that there exists a family of systems whose number of states is linear to n, and such a system is not actively safe, but it is 2 to the n active predictable. To prove the second result, let's look at this system, which has n plus 5 states. And in this system, the set of observer events are 0, 1, 2 until n, all are controllable. And we use sigma r to represent set of observer events bigger than r and gamma I smaller than r. And in this system, when we enter Q, which means the system becomes not predictable with FU entering the same state. And when we enter P prime, system is still predictable, but with the occurrence of the fault. So we prove that we cannot find a controller such that a system can avoid both Q and P prime infinitely, which means that it's actively safe, because in this part there is no fault. But we prove that we can find controller that can avoid to enter to Q at the price of entering P prime after 2 to the n steps. So in this system, when we stay in any state as R to avoid to enter Q, the next event cannot be R. Here we use for each state S0, S1, each state as R, we use binary number to represent the fact that when the value is 0, then with current observations, SR is not, the corresponding state is not possible. And when the value is 1, which means it is possible. Now we'll show this controller that can avoid to enter Q, but need to enter P prime after 2 to the power of n steps. So first, it chooses 0, and when it chooses 0, either we stay in P because gamma n include 0, or it enters as 0. When it enters as 0, next event cannot be 0, so it chooses is 1, and for this event, either stay in P or we enter as 1. When we enter as 1, next event cannot be 1, and so binary becomes 1, and the next it chooses 0, which means that either we stay here or we stay here as well, because gamma 1 also includes 0, or we enter as 0. So both of them becomes 1. We cannot choose the next event as neither as 0 nor as 1. So it will next we choose 2, and we continue this procedure, and we prove that after 2 to the power of n minus 1 steps, we reach this situation where all states as are possible, which means the binary number of them are 1. And in this situation, only option we have to avoid to enter Q is n. So system has to go into the P prime after 2 to the power of n steps. So we prove that this system is actually 2 to the power of n active predictable, but not actively safe. Okay, finally, I will talk about some perspective of our work. There are three future directions we are interested in. First one is that we want to quantify the faultiness to find an active predictor that can minimize discrete error. And the second one is what we want to extend to the notion of pre-diagnosis, which is combination of predictability and diagnosability. Finally, we also want to study the active predictability of probabilistic systems and with concurrency as well. So thank you very much for listening to my talk.